everyone. In this video, I would like to start talking about the shell method in more detail. So we'll do an example. In the last video, we introduced the shell method as a way how we could take cylindrical shells to approximate volumes. So say that I'm integrating across my little region, and I'll have a cylindrical shell here. The cylindrical shell there. Then I'll have another cylindrical shell above it. That might go a little higher depending on what our function does. And then that will go around as well. And then we keep on going and going until we get higher and higher, and these cylindrical shells replicate a function. So say this is a function that looks like that, right? Like that. And then we rotate it, and then we get that mirror image kind of, and we want to find the volume in there. When we rotate it, we can use the cylindrical shells method to determine that volume. So we covered earlier about how we did this cylindrical shell method, and we remember that our volume was equal to the integral between a and b. Sorry, that's almost an alpha. Make that an a. And that was of 2 pi x f of x dx. And this this kind of boundary that we've made is a boundary from the edge of our cylinders. So if I'm making an integration across a washer, say, so this is maybe the function that I'm integrating about that I'm going to rotate around with my cylinders in here that are going to be rotated. Those are my cylinders. Then that's the interval between a and b. And if one of my bounds that is stated in the problem happens to be the y-axis or the x-axis, depending on what we're integrating over, then that will be from 0 to b. All right, so now let's try an example. So for this one, I would like to find the volume obtained by rotating y equals x to the 1/3 power, y equals 0, and x equals 1 about the y-axis. As always, what I'd like to do is I'd like to draw this out. That can always help us determine what we need to do. So there is our axes. And if we remember what our function x to the 1/3 looks like, it looks a lot like our cube root or our cube function, but turned on its side. So we get something that looks something like this here. So we get something that looks like that a little bit. And we also have x equals 1. So we're going to have this line here. And then we're also, it also says here y equals 0, so that's just the x-axis right there. And we're integrating about the y-axis. We're going to rotate around there. So now let's find our intersection. So we set x to the 1/3 equal to 1. Of course, that answer is going to be 1. So here, as you may have already guessed, we have our point here, 1, 1. And now you can see that we are going to be integrating between 0 and 1 when we plug that into our integral. But now let's draw kind of what we're going to be doing in terms of our cylindrical shell integration. So here is the other side of it. Let's say this is here -1. So we're going to have our cylinders. Here's a cylinder. I'll try to draw this in a somewhat nice fashion. So we'll get this. And then this will, I'm kind of going to go over the problem statement, kind of go down here, back there, and here's the other side of our cylinder, and then we go back up here, we're going around up here, and then we, of course, go back around, but we're also going to have these cylinders in here. So it's going to look kind of like a big, weird shaped ball, almost like a funnel. although the edges aren't going to be straight. So that's kind of what it's going to look like. Now let's perform our integration. So the volume, as I said, is equal to the integral between a and b of 2 pi x times f of x dx. Now, as I said earlier, we're integrating about between 0 and 1. We're finding this volume here, and then we're rotating that about the axis. So let's perform this integration. So that gives us 2 pi, we can pull that 2 pi out, times the integral between 0 and 1, x times x to the 1/3 is x to the 4/3 dx. Now some simple monomial integration and application of the fundamental theorem of calculus. This gives us volume being equal to 2 pi times 3/7 x to the 7/3, evaluated between 0 and 1. 1 to the 7/3 is 1, and 3/7 times 1 is also 1. So that gives us 2 pi times 3/7, which turns out to be 6 pi over 7. So this volume that we determined in there is 6 pi over 7. Thank you very much for watching this video of 3 deviations. In the next video, we're going to do one final example, really tricky example involving the disk and shell method. And after that, we're going to be looking at some physics applications in work integrals. Thank you for watching, and we'll see you guys in the next video.